Hi everybody, welcome to 6.2 tutorial. Now this 6.2 tutorial is going to cover one-dimensional collisions and also 2D collisions. So everything that we've done since for 6.1 and 6.2. Alright? Alright, let's go ahead and go on. So the basic rules of this exam is that you have to assume that the collision is not perfect unless told that it is perfect. So the problem will state it's a perfect collision. Okay, and that's when you could assume that the coefficient of restitution E is equal to 1. Okay. Find the final velocity of both objects after the collisions. Likely it'll say, if it doesn't want you to find both objects, it'll just say find this one velocity. Find the accelerations of both objects during the collision, so how much their velocities are changing during the collisions. Find the change in energy during the collision. Find the power of the collision. And graph the velocities for both objects on a V versus T graphs. And graph the total change in energy, the initial energy versus the final energy on the graph, which is going to tell you the power. So this graph is going to tell you the power, and this graph is going to help you figure out the acceleration. So yeah. Okay, let's go on. I'll show you what we have to do. And you probably saw a lot of this in 6.1 or a problem similar to this in 6.1. But let's go ahead and do this together. Now, here it says this is a 1D collision problem. Okay, it says there's a car moving at 4 meters per second to the right, and it makes a perfect collision with another car that is 8 kilograms moving to the left at 8 meters per second. And they state the collision lasts 0.01 seconds. So, since it's a perfect collision, we could assume this coefficient of restitution is equal to 1. Alright. Let's start off with making a list of variables that we have. Okay. We have a 4 kilogram object, and it's got an initial velocity of positive 4 meters per second, and the other car is 8 kilograms, and it has an initial velocity of negative 8 meters per second. And we need to find both of the final velocities for the 4 kilogram car and the final velocity for the 8 kilogram car. So let's do that first. Okay, so I'm going to move in here. Let's make up our little picture. So we have a 4 kilogram object moving to the right at 4 meters per second. Animal Crossing. My nephew just called me. Okay. Now the other object is 8 kilograms, and it's traveling to the left at negative 8 meters per second. After they collide with a perfect elastic collision that lasts 0.01 seconds, we need to figure out the 4 kilogram object's final velocity and the 8 kilogram object's final velocity. So what do we do when you have one equation and two unknowns? You need another equation. Now I showed you in 6.1 what happens when you try to use energy to do that. You can do it, it's just a little complicated, and you end up having to, find the quadratic and then making an evaluation whether the velocity, the positive version of the quadratic or the negative version of the quadratic is actually the solution. So it's better to use a coefficient of restitution. So that's what we're going to do. So let's go ahead and write the coefficient of restitution right here. So that's a perfect collision. We're going to put the negative in front. And so we are going to put the final velocity of the 4-mass object first. And we're going to subtract that from the final velocity of the 8-mass object. And the final velocity, the initial velocity of the 4-mass object is 4 meters per second, which is positive, and we're going to subtract that from the negative 8 meters per second, which what we're going to end up getting is negative v final 4 minus v final 8 over, what is that, 8, 9, 10, 11, 12. So 12 meters per second. And we're going to divide that up onto the other side. So this is going to be 12 meters per second equals negative v4 final 4 minus v final 8. And we're going to multiply everything by a negative here, by negative 1. And what we'll get is a negative 12 meters per second equals v final 4 minus v final 8. Let's just add that v final 8 onto the other side. So we're going to add that onto the other side. V final 8 equals v final 4. So let's go ahead and plop this. Actually, I'm not going to circle that. Let's go ahead and plop this. Actually, before we go ahead and start substituting this equation into here, let's refine this. So this is going to be a positive 16 kilogram meters per second. Positive 4 times positive 4. This will be 8 times 8, which will be 64 kilogram meters per second. That is negative. That's going to be equal to 4 kilograms V4 final, V final 4, plus 8 kilograms V final 8. 16 minus 64. So 16 minus 64. 48. So let's go ahead, and this is going to be negative 48. And this is, well, we're going to need some room. And so that's what we'll have. Now let's go ahead and start substituting this in. So let's take this guy right here. We're going to take this guy up to here, and we're going to take it and put it over to here, and we're going to plop it right into there. We're going to just place it. So substitute this whole thing in. Okay. Now, what we have is negative 48 kilogram meters per second equals 4 kilograms, negative 12 meters per second, plus V final 8 plus 8 kilogram V final 8. Okay, so let's do this. So this is going to be negative 48 kilogram meters per second. 4 times negative 12, negative 48 kilogram meters per second, plus 4 plus 8, that's going to be 12 kilogram meters. Actually, it'll just be 12 kilograms V final 8. We're going to add this on to the other side, and we are going to get 0. So V final 8 is going to be equal to 0 meters per second. So that this big object right here is going to come to a stop. Okay? So now we know that that guy is going to come to a stop. So that's the initial velocity. That's the final velocity for the mass 8 object. Now, using this other equation, since it's right there, we're going to plop it right into there. And when we do that, we'll get negative 12 meters per second plus 0 meters per second, and that's going to be V4 final, V final 4. So V final 4 is going to be equal to negative 12 meters per second. So that is the final velocity for the 4 kilogram object. Okay. Incidentally, we could have plugged this 0 meters per second right in to 8 right here. Then we would have had negative 48 divided by 4, and that would be negative 12. You could have done it that way too. But I just put it right in here because it was right there and I saw it. Okay, so let's say, let's do the energy part. So let's find the change in energy during the collision, which it asks us to do. Okay, well, this is an energy part, so there are no changes in potential energy since this is on flat ground. So what we're going to do is we're going to sum up the initial kinetic energies, set it equal to work, plus work, and set it equal to the final kinetic energies, which the initial kinetic energy is the initial energy, and the final kinetic energy is the final kinetic energy. So work is going to be equal to the change in kinetic energy. Actually, you know what? I'm just going to sum up the kinetic energies to begin with here. So this will be 1/2 4 kilograms 4 meters per second that we're going to square, plus 1/2 8 kilograms times negative 8 meters per second that we're going to square, I'm going to scooch this guy over so I have a little bit more room. Okay, and this is going to go plus work, which is going to be equal to the final kinetic energy for the 4 kilogram block, which is 4 kilograms times negative 12 meters per second that we're going to square, plus the 1/2 times the 8 kilogram block's final kinetic energy, which is just 0 meters per second that we're going to square. Okay. I will take this guy and I will move it up here. Okay. Okay. In fact, I'll just move it over. Oh, no, we're not going to worry about it for right now. So, what we're going to have is 16 divided by 2, which is 8. So this is going to be 8 joules. This is going to be 64 joules times 4. 64 times 4, which is 256 joules. Plus work, which is going to be equal to 144, so 12 squared, 144 times 4 over 2, which is 2. 144 times 2, which is 288. I knew that. Okay, so hold on a second. There's something that I feel is not right. 64 times, let's see, this is 64 times times 4. 256. This is 16 times 2, so this should actually be, this is not 8. This should be 16 times 2, which is 32. So this should be 32. Joules. Okay. And again, this is 144 times 2, so that's going to be 288 joules. Glad I double checked that. So this is 288 joules plus work is going to be equal to 288 joules. So work is just going to be equal to 0 joules. So no energy is entering or leaving the system. Okay. All right. So now that we have that all done, let's go ahead and calculate. Let's do the other parts of this. Let's use the velocity versus time graphs to help us figure out the accelerations of these objects during the collision. I'm going to use green is the first object, and red is the 8 kilogram object. Let's do the 8 kilogram object first. And I'm going to just mark this as positive 12 to negative 12 meters per second. And again, this is 0.01 seconds, and this is 0.01 seconds. So, okay. Let's go ahead. It starts out at negative 8 meters per second. So the red guy starts out, this is 2, 4, 6, 8. So this is negative 8 right here. And it ends up at 0 over that period of time. So this acceleration for the 8 kilogram object is going to be equal to, and it's going up by 8, so that's positive 8 meter per second change in velocity over 0.01 seconds. So that's 80 meters per second squared. So that's the positive of that. In the for the green guy, it starts off at 2, 4, so this is going to be positive 4, and it ends up traveling at negative 12 meters per second, which is down here. So, which is way down here. So this guy is dropping a huge amount. It's dropping by 12 and then another 4. So the acceleration for the 4 kilogram object is, what is that, negative 16 meters per second change in velocity over 0.01 seconds. So that acceleration is negative 160 meters per second squared. All right. For the power, well, that's easy. Since there's no change, there's the initial energy is 288. I'm just going to put positive 288 right here, joules, and that is not changing the whole period of time. So power, which is equal to the change in energy over the change in time, that's going to be equal to work divided by time, which is going to be equal to 0, we found out, over 0.01 seconds, which is 0 watts. So power is equal to 0 watts. There is no energy entering or leaving the system. Okay. And so that is how to do, it's pretty close to page 1 on your tutorials. Okay. I like these problems, and this problem is a really good problem because it interweaves a lot of things that you've already done before, right? It interweaves energy with momentum, and then you have to use your numbers to actually figure out those accelerations during the impacts. So that is a really important way to get all of your concepts of motion to work together. Okay. The only thing we could do more is make you do a force diagram, And I don't want to overload you, and I already feel like this is kind of on the edge of that. It also helps you start thinking about what power really is, where power is the rate of change of energy entering or leaving the system. Okay? Okay. Let's do another problem. I'm going to clean this up. Hold on. All right, here is the next problem. You have a car moving to the right at 4 meters per second. So in fact, this is the same problem that we just did, except this case you are not given that it is a perfect and elastic collision. In fact, we're going to find out by doing this problem that it is an imperfect elastic collision where there is going to be energy lost. And so we already know what the answers should be. So is 4 kilograms moving to the right at 4 meters per second. So it's the same problem that we just did. However, it gives you a flawed final velocity, and I'll show you what I mean by that. So when I'm writing this out, positive 4 meters per second. Now the 8 kilogram object, just like in the other problem, is moving to the left at negative 8 meters per second. And they say after the impact, okay, the 4 kilogram object, we don't know what its velocity is. We're going to have to find that out. That's what they're asking for. So we'll just call that V final. But we're given that the 8 kilogram object is moving to the left at negative 2 meters per second. Okay? So there is something wrong with this. Okay? Because we know if it's a perfect collision that 8 kilogram object should have come to a stop. Okay? So, but this 8 kilogram object is still moving to the left. So it seems like there might be a loss of energy during this impact. So my guess is right now that work is going to be equal to 0. And then I want to put that, I want to compute the coefficient of restitution and show you what happens when you have an actual work that is different from 0 and how that affects the coefficient of restitution. Okay? So we're using this problem to kind of teach you. Now we have to do everything that we did on the other problem. Find the accelerations of both objects during the impact, figure out the initial energy, figure out the final energy, figure out work, plot those things, and plot the V versus T graph, and that'll tell us the accelerations, plot the initial energy versus the final energy over here, and that'll tell us the power. But I'm going to add on to that by showing you what happens when the coefficient of restitution is working with this flawed type of problem. Okay, so just like before, we had worked out that this energy right here is going to end up being negative 48 kilogram meters per second. So we already know that, and I'm doing this for the sake of time, since there is no change in these problems. I'm going to write that number again, but smaller. So we know this is negative 48 kilogram meters per second. Now, this is going to be 4 kilograms V final, which is what we're going to solve for first, and minus 16 kilograms meters per second. So we're going to add this 16 onto the other side. And when we do that, we're going to get negative 30, what is that, 2 kilogram meters per second. So, yeah, 32. And that's going to be equal to 4 kilograms V final. So negative 32 kilograms meters per second divided by 4 kilograms. That's going to be equal to V final. And V final is going to be equal to divided by 4, 8. So again, on the other problem, this was negative, it should be negative 12 meters per second for this V4 object, which is green. So got to remember that that's the green object, and that 8 kilogram guy is the red object. Okay. So, all right. Well, we found the first part. We found what they're asking for. Let's see how this works out for our energy. Okay. Now, again, for the sake of time, we've already done this part of the energy part, the very first part. The potential energies aren't changing. So the initial sum of the initial kinetic energy is the initial energy plus work, which is going to be equal to the sum of the final kinetic energies, which is the final energy. And we know the sum of the initial kinetic energies from this problem, which is no different from the other one. The initial cases are the same. This is going to work out to 288 joules. Okay? And that's going to be plus work, which is going to be equal to 1/2 our 4 kilograms times the negative 8 meters per second that we're going to square, plus the 8 kilograms final kinetic energy, which is negative 2 meters per second, that we're going to square that guy. So this is going to be 288 joules plus work. This is going to be 64 times 2. 64 times 2, which is 128. 128 joules. Plus, this is 4 divided by 2. 4 divided by 2 is 2 times 8, so this is going to be 16 joules. So you could already see there's going to be a big difference in energy. So 8, 9, 10, 11, 12, 13, 14. So that's 134 joules. You know what? I don't trust myself. I know I just counted 128 plus 16, 144. I'm glad I don't trust myself. That's what I get for trying to trust myself. Tell me you're not the same. Okay, so work is going to then be this final kinetic energy. This is the final energy, by the way. And this is the initial energy. Okay. So that's going to be 144 joules minus 288 joules. So we are going to have a loss of energy in this system, which is going to be 122 joules. And that is correct. I'm sure that is correct. Okay. All right. Now, we didn't have to do this part, but this is part of your lecture, so I want to point this out. Let's figure out what the coefficient of restitution is. We know we have a loss of energy. What I'm going to do is I'm going to put the final velocity for the 4 kilogram object first, which is going to be negative 8 meters per second. And we're going to subtract that from the final velocity for the 8 kilogram object, which is 2 meters per second. Okay, on the bottom, and we got this negative in front, on the bottom we have the initial velocity for the 4 kilogram object. So this is 4, yep, that's correct, minus the initial velocity for the 8 kilogram object, which was negative 8 meters per second. All right, wait, the units here are correct. I want to do something and double check everything before I move on. And this, guys, 2 meters per second afterwards should be negative. All right. So now let's go ahead and solve for those values. Don't forget the negative from there. So this is going to be -8 minus a -2, which is going to be a -6 meters per second on top. 4 minus -8 is going to be 12 meters per second. This negative, so this is going to be equal to negative times a negative is a positive, so it looks like that E is going to be a half. It looks like it's going to be 50%. So 0.5. That is what that coefficient of restitution is. I shouldn't have said it was 50%, but the coefficient of restitution is 0.5. So let's see how that is related to our energy stuff. Okay, so if we take our initial, our final energy, which in this case is just, and we do a proportion of final energy to initial energy, okay? And that is our final kinetic energy in this case, which is our initial kinetic energy. Putting together what E really is. And our final kinetic energy is 144 joules, and our initial kinetic energy is 288 joules. So if you look, which you get 0.5. Now, I think it's a bit of a, it's a coincidence in this case that these two things are equal, okay? It's not always equal. But what I'm saying is there is a relationship between these two things, okay? That coefficient of restitution is related to the interpretation of final energy over initial energy, okay? So, anyways, I just thought I'd point that out, okay? That's how you should interpret it. Okay, let's go ahead and plot our velocities. So this is 12, this is -12, 0.1 seconds, just like it always is. It's not always 0.01 seconds. Okay, 0.01 seconds. Okay, so our starting velocity for our 4 kilogram object, I'll do that here first, is right here. That's +4 meters per second, and it ends at a velocity of -8. So that's 2, 4, 6, 8. So that's going to be -8. So it's going to look like this. And so that acceleration for the 4 kilogram object, it's dropping by, I'm just making sure that that is -8. So it is dropping by 8 and another 4, so that's going to be -12 meter per second change in velocity over 0.01 seconds. So that acceleration is -120 meters per second squared. The red, the 8 kilogram mass, is starting off at -8 and then it's ending at -2. So it's increasing in its acceleration is positive. So that's the 8, and this is going up by 2, 4, 6. So this is a +6 meters per second over 0.01 seconds. So this is going to be a positive acceleration of 60 meters per second squared. All right. Okay, let's go ahead and plot the energies and work out the power. So the power starts out, and we'll call this 288 up here. 2, 4, actually, let's change it to 288 right here. 288 right there. And it ends at 144. So this is going to be dropping by the amount of work. So the power is change in energy over change in time. That is work divided by time, which in our case, our work was negative 122. So that's going to be equal to negative 122 joules over 0.01 seconds. So the power is going to be negative 122.00 watts. So it's dropping a lot of power. A lot of power is leaving that system per second. So, okay. I hope you are learning from this. So this is kind of like your page number 2. Let's move on to another problem. This is an elastic collision problem. All right. And I'm just going to get into it to drawing the pictures. It looks like we have a 6 kilogram block that is moving to the right at hold on one moment. The problem should have stated that this is a 6 meters per second to the right. So it's moving to the right at 6 meters per second. So there we go. And we have another block which is 4 kilograms moving, we have another block that is 3 kilograms moving to the left at 3 meters per second. Okay. After they hit, it says there is an elastic collision, which means we cannot use this coefficient of restitution. 6 kilograms plus, actually, hold on, I don't know that for sure. I know it's predictive for elastic collisions. Let's not worry about that for right now. We're not going to need it anyways. So after they hit, they're going to combine to become a 9 kilogram object moving at some final velocity. Okay? So this is going to be 36 kilogram meter per second. That's positive. This is going to be a negative 9 kilogram meter per second. And this is going to be a total of 9 kilograms V final. 36 minus 9, 27. So this is going to be 27 kilogram meters per second. That is positive. That we're going to divide by 9 kilograms. And that is V final. That is 3. So the final velocity after the impact is equal to positive 3 meters per second. So both objects are traveling at that final speed. Okay. Let's go ahead and plot the energies now. Okay. Their potential energy in these problems aren't changing. They're not going up hills or any of that kind of stuff. So we're going to sum all the initial kinetic energies plus work, and we're going to sum all the final kinetic energies. And what we found out earlier, whenever there is an inelastic collision, there's a loss of energy. So let's see if that's true. So let's go ahead and put in 1/2 times 6 kilograms and 6 meters per second that we're going to square, plus the initial energy for the 3 kilogram object, negative 3 meters per second, that we're going to square, plus work. I'm going to run out of room. Always run out of room. Okay. That's going to be equal to the final kinetic energy for this 6 kilogram object. And they both have the same speed. But they do not both have the same kinetic energy. Just because they have the same speed, they don't have the same kinetic energy. All right. So this is going to be 36 times 3. 36 times 3. 108. And this is going to be 9 times 3 divided by 2. So I'm going to do that next. So this is 108 joules. So 9 times 3 divided by 2, 13.5. So plus 13.5 joules. I don't think your problems have fractions in them, mind you. So that's going to be 9 times 3, which is going to be 27 joules. And this is going to be 3. So it's going to be 9 times 3 divided by 2, which is just 13.5. Why? I already know what that number is. 13.5 joules. Its initial energy is negative. Its initial velocity is -3. Its final velocity is +3. So that's kind of funny. Okay. So we're going to get on the right side 108 plus 13.5, 121.5. 121.5 joules plus work. And this is going to be 40.5 joules. So this work is going to be a loss of energy, which I think is most of the time for collision problems. In explosion problems, it's the opposite. So in the next problem, you'll see when two things are together and they explode, there's a positive work. So minus 40.5 equals 81. So the amount of energy lost is 81 joules. Okay. All right. Again, we're going to use red as the second object. Green is going to be the first object. And I'm going to, let's go by threes. So this is going to be 3, 6, 9, 12. I'm just going to put 12 right here. And this is going to be 3, 6, 9, 12. So this will be -12 right there. And 0.01 and 0.01 over here. Okay, let's plot some things. So this green guy starts off at +6, says 3, 6. So this is +6 right here. And it ends at +3. So it's going to end at +3. I'm going to use black because both of them are ending at +3. So the green guy is doing this. It's starting right here and ending right here. So the acceleration of the 6 kilogram object is it's dropping by 3 meters per second over the 0.01 seconds, which is going to be -30 meters per second squared. The red object is starting at -3, which is -3, and it's going up to +3. So that 3 kilogram object its acceleration is going to be 3, so it's going to be positive 6 meters per second over 0.01 seconds, which is going to be positive 60 meters per second squared. All right, let's do the power for this guy. His initial energy is right there. It's the initial kinetic energy in this case. The final energy is right there, which is 40.5. This is not going to be exactly proportional, but we'll put 121.5 up here. So that's 12. So it's going to be 2, 4, 6. So it'll be somewhere around like right. So if this will be 60, it'll be about right here. So this will be 40.5. 120, and then so the power is going to drop to by 40.5, and so this guy's power is going to be negative 81 joules divided by 0.01 seconds. So that is going to be, and I'm just double checking, 81 divided by 0.01. Yeah, that's what I thought. So it's going to be a lot of wattage, 8,100 watts. Okay. So that is similar to your third problem on your homework, your tutorials, I should say. Okay, let's move on. This one is an explosion problem, and we already did this in the 6.1 lecture. It's the Amy and Gwen problem, but we're going to do it again because it's a good explosion problem. All right, so you have Amy, who is 60 kilograms, and you have Gwen, who is 20 kilograms. They are both not moving, so they're standing still. I think your problem, they are moving initially. Okay, and that all that does is just they're together moving. So technically, I should probably point this out. In your problem, they are one object. So I'm going to present them as one object. So 60 plus 30 kilograms. And they are not moving. In your case, they are moving, so you just add those 2 kilograms and then multiply it by that. So it doesn't change much. Now, after they explode, 60 kilograms, Amy's moving to the left at 6 meters per second. And poor Gwen, she's going to be moving to the right, likely at some speed. So this is going to be 0 kilogram meters per second, and this is going to be negative 360 kilogram meters per second. I'm going to center the screen, and this is going to be plus 20 kilogram meters per second. So add this onto the other side, so you got 360 kilogram meter per second equals 20 kilograms. And I don't know why I put a meter per second there. That should just be V final. V final. So 360 kilogram meters per second divided by 20 kilograms is the final velocity. So the final velocity of that is going to be 18 meters per second, which is huge. Poor Gwen. I think that's close to 40 miles an hour. This is the reason why physicists should not design problems. Okay, now that we've done that, let's do the kinetic energies. Again, these problems, they're not gaining any potential energy. I think in your energy problem over here, which is similar to this guy, it is. So there is a potential energy there. Plus work equals to final kinetic energy, but not this guy. So in the beginning, since they are not moving, I'm just going to put 0 joules plus work, and that's going to be equal to the final kinetic energy, which is going to be 1/2 60 kilograms times -6 meters per second that we're going to square, plus, and I do this quite frequently, I'm going to run out of room, plus 1/2 times 20 kilograms times 18 meters per second. That's a lot of kinetic energy. All right, so the work on this side, which is just by itself, work plus 0, that kinetic energy for Amy after the push is going to be 36 times 60 divided by 2. So that's 1080. So this is 1080 joules. And Gwen is 18 times 18 times 20 divided by 2. So that's 3240. So this is 3240 joules, which is enormous. Right. So 3240 plus 1080, 4,320 joules of energy. Joules of energy. Let me just double check that. Yeah, that looks good, which is positive. So that is what an explosion is. It's a release of energy. It's not energy, it's energy added to the system. Okay, and that's by their two forces, which was their impulses and all that other stuff. So if we knew the displacement of their hands during the push, or we knew, so we would need that to figure out what the impulse is. Can we figure out the impulse? I think we might be able to. Okay, anyways, let's go ahead and work on here. Work on this. I'm going to come back to that. Let's see if, after I do this and plot the stuff, I'm going to just come back and see if we can plot the forces. Okay. So let's use, Amy is going to be green. It's the left one, and the right one is Gwen. Okay. So Amy starts out not moving. So this is going to be, let's go by threes. So this is going to be positive 3, positive 6, positive 9, positive 12, and positive 15, and positive 18. And this is going to be negative 18. Right there. Okay. And this is positive, this is negative 3, and this is negative 6, negative 9, negative 12, negative 15. And this is 0.01 seconds. This is 0.01 seconds. Okay, got everything ready to go. So the green guy starts out not moving. So Amy starts out not moving, and then she's moving at 6 meters per second to the left. Okay, so Amy's, and I need some room for this, so this is going to be Amy. Amy's acceleration is she's changing by 6 meters per second to the left over the period of 0.01 seconds. So this is going to be a negative 60 meters per second squared. Gwen starts out at 0 and ends up at positive 18 meters per second. So before I do that, I'm going to move Amy's stuff down. Give me one moment. Since I just moved Amy's stuff down here for her acceleration. Gwen starts off not moving, and then she's moving at positive 18 meters per second. So the slope of this line for Gwen is going to be positive 18 meters per second divided by 0.01 seconds, which is a positive 180 meters per second squared. Okay. Now for the energy. Well, it's pretty easy. They both start off not moving, and I don't know, we'll call this positive 4320 up here. So that's 4320 joules. So ends up going up here. And so that's that power is gonna be positive 4320 joules divided by 0.01 seconds, which is, that's going to be 43200 watts, which is huge. That is a huge amount of energy being added to that system. So that's a large wattage yeah. All right. Let's try, we're almost done. Okay. So let's do this problem, okay? Now, this is similar to your problem. I think your problem is very close to this. But here's a problem. It's almost a true story. I was skateboarding and a little kitty cat dropped onto me and scared me, and it landed on me and I fell to the ground. I was a little kid at the time and I was crying. And anyways, so this problem is there's a cat who's 2 meters up and he's going to land on your head. 2 meters difference between your head and the cat. So consider like your height as where your head is 0 meters, and you're 60 kilograms, so you're about 130 pounds. And you're skating just to the right. Okay? Okay, so looking at this, there's no velocities. We do have masses, but there are no velocities. So we can't do this starting with momentum. We have to start with energy. And let's start with the kitty cat's energy. So the kitty cat is up in a tree, not moving. It doesn't say that, but let's assume that. And so no springs are touching. He has no initial kinetic energy. Since he's just falling without air friction, there's probably not going to be any work. But right before he hits your head, he's got a kinetic energy. Your head is a height of 0, and no springs are touching you. Since the only thing acting on the cat, if we did a force diagram on the little kitty, little meow meow, put little whiskers. The only thing acting on the cat in this force diagram is mg, okay, which is covered here. So the cat's in free fall. So the potential energy, the initial energy is only potential energy, and the final energy is only kinetic energy. So the kitty cat's mass times gravity times height is equal to 1/2 the kitty cat's mass times velocity squared. The little m's are going to cancel out. We're going to get 2gh which is equal to v squared, and then square root both sides. And when we do that, we're going to have our velocity. So let's go ahead and put in 2 times 9.8 meters per second squared times the height, which is 2 meters. So we're going to figure out the velocity of the kitty cat right before he lands on your head. Okay? So what is that? 4 times 9.8 and square root it. So 6.26. So 6.26 meters per second. So that's how fast the kitty cat is going right before he hits your head. Okay. Okay. So the guy is moving to the right at 6 meters per second. The cat is falling down in the y direction. So this is the kitty cat's y direction velocity. So the cat's y direction velocity before the impact. So this is the initial velocity of the cat in the y direction, which looks like icy. Okay, that's weird. So let's make some diagrams. So here we have the skater, which is 60 kilograms. He or she, since it's autobiographical, it's me. He's moving to the right at 6 meters per second. Now the kitty cat, when he's falling, he is not moving in the in the x direction at all. So that is 0 meters per second. Now after they hit, they're going to combine masses. Which is going to be 65 kilograms, traveling at some final velocity in the x direction. So for both objects. Okay. In the y direction, the person, the ice skater, me, I'm not moving, but the kitty cat is moving at 6.6 meters per second downwards. Okay. I'm just going to double check that. That 4 times 9.8 square root 6.26. Glad. See? That's why I don't trust myself. .26 meters per second. So the kitty cat is traveling down at negative 6.26 meters per second when he hits. Now, after they hit and combine, so there's still an impulse, and I forgot to add the little impulse here, in the x direction here. So plus an impulse, and this is going to be plus an impulse in the y direction. However, in the y direction, after they hit and combine, 60 plus 5 kilograms, they are not going to be moving in the y direction. They are going to just be moving in the x direction. And so what you find out is this is 36 kilogram meters per second, and that's equal to 65 kilograms v final. And so we find out what the velocity of both the kitty cat and the person is. There's 36 kilogram meters per second divided by 65 kilogram meters per just kilograms. And so this problem is cool because there's an impulse in this. It won't make sense if there isn't an impulse, okay? But not in the x direction. So 36 divided by 65, that is 0.55, so 0.55. So a little bit over half a meter per second. So that is their final velocity after the impact. However, in the y direction, something weird is happening, right? And I'll sum this up here real quick. So 6.26 negative times 5. So that's negative 31.3. So the kitty cat is the only one moving in the y direction, which is negative 31.3 kilogram meters per second. And that, I'm going to leave a space, is equal to 65 times 0, so which is 0 kilogram meters per second. So what do you find out? There has to be an impulse. When that cat landed on me, it crunched down on me, and I had to push up in order to keep my entire velocity as 0 in the y direction. So you had to push up. I had to push up over a period of time. So what you find out is that if I add this guy onto the other side, and if I knew the time of the impact, and I could have supplied that 0.01 seconds, 31.3 kilogram meters per second. What you find out is that I had to push up over a period of time at 31.3 Newton seconds, which is 31.3 Newton seconds, to bring the kitty cat to a stop. Okay? So this is a really cool problem, and I really love this problem. All right, your problem is, it's not too much more complicated. It starts out with a potential energy, and it ends with a potential energy, and there's an impact in the impact in between. So it starts out with a potential energy, and when it ends, it's ending at a kinetic energy, and then there's an impact, and then you go back to energy to figure out how high it goes back up. So it's kind of cool. You go from energy to momentum and then back to energy. Okay? All right. Moving on. Here is that last problem from 6.2. Well, it's not the last problem, it's second to last problem from 6.2. And it's that it is that inelastic collision problem. So in this problem, we're going to go ahead and start on plotting out this stuff. In the x direction, we have a 1,000 kilogram VW moving to the right at some velocity. The Cadillac, which is 2,000 kilograms, is not moving in the x direction at all. After the impact, they are going to be combined together, which is going to be 1,000 plus 2,000 kilograms, moving at some final velocity in the x direction. In the y direction, the VW Bug, the Volkswagen Bug, has no initial velocity in the y direction. However, the Cadillac which is 2,000 kilograms, is traveling upwards. So upwards, and this guy's moving to the right, at a positive 3 meters per second. And when they hit and combine, that's going to be 1,000 plus 2,000 kilograms. They're going to be moving they're going to be moving upwards at some final velocity. Okay? Okay. Now, after they hit, okay, so this is they're going to hit right here, and we're going to write 3 kilograms, K anyways, this is both objects combined together. We're going to set up a coordinate system just like I taught you. What just happened? Right there, not exactly at the center, close enough. Plus y, negative x, negative y. So after they hit, they're going to be moving off at some final velocity, right? Right, v final, which is what we need to solve for, right? Now, we know the final velocity in the x direction. Actually, we know the angle, which is 35 degrees. So it's moving to the right at v final cosine of 35 degrees. That is the final velocity in the x direction. That is this guy. In the y direction, they are moving upwards, the v final y, at v final, which is going to be, well, it'll be positive sine of 35 degrees. Okay? So we're just going to replace these two velocities with that. Okay? Now, let's go ahead and start putting some stuff in here. So this is going to be 1,000 kilograms of velocity of the VW, and this is 0, and this is v final x, which so this is going to be 3,000 times v final x, which we know is this. So this is 3,000 kilograms v final cosine of 35 degrees. So right now we have to solve for this. But we have another unknown right there. We need v final. All right. The only way we get it is with another equation, which is right here. So this is going to be 0 momentum. This is going to be 6,000 kilogram meters per second. That is positive. And this is going to be equal to 3,000 kilograms v final sine of 35 degrees. We're going to divide this on the other side, which we're going to have as a positive 2 meters per second, and that's equal to v final sine of 35 degrees. So v final is going to be equal to positive 2 meters per second over the sine of 35 degrees. So this is probably going to be close to 4. That's what I'm guessing. So that's the overall final velocity that we're finding. So 2 divided by 35 sine in parentheses equals, which is equal. So 3.49. 3.49. So this is positive 3.49 meters per second. All right. Well, now that we have that, we could just take that that positive 3.49. Actually, it isn't positive. It's just unitless. It's just a number. All right. So this is, we're going to put this guy right into here. Okay. All right. So this is 1,000 kilograms VW, and that's equal to 3,000 kilograms times 3.49 meters per second times the cosine of 35 degrees. So that VW is going to be equal to 1,000 kilograms. And this is going to be 3,000 times 3.49 meters per second times the cosine of 35 degrees. Okay, so let's multiply that all out. Let's go from right to left. So cosine of 35 degrees times 3.49 times 3,000 equals. Now let's divide that by 1,000. 8.58. So the VW bug was moving at 8.58 meters per second to the right. And that's how you do these collision problems where it's an inelastic collision, where your problem that you have for your tutorial is much easier than this one, I would say. You're given the two initial velocities here, and you just have to figure out v final and that angle that they hit with. So it's kind of like this problem, but in reverse. Okay. Well, this is 6.2 tutorial. Okay. I hope you have a wonderful day, and please get started on this tutorial. It's a good tutorial. Again, it integrates a lot of prior knowledge, so you're going to have a really good understanding of momentum and energy and how that relates to acceleration and power. You're going to be really good at understanding your concepts. Will be really great. Have a good day.